Okay, electric current. It's, like I said, its letter is I. And electric current is just the flow of charge. So when we talk about electrostatics, it's the buildup of charge on an object. It's the charge that builds up when you scuff your feet across the carpet. And then when you touch a doorknob, that build-up charge on you switches over, jumps over to the doorknob. That purple jacket that I wear, it, whatever its lining is made of, it just causes a ton of buildup of charge on me. So when I come home at night and reach for the light switch, I usually blow the light bulb if I don't touch something first after I take my, after I take my jacket off. So electrostatics is just the buildup of charge on a surface of an object. But when we talk about electric current, we're now allowing that charge to flow. And so it's the flow of charge from one object to another. In order for flow to happen, flow of charge to happen, one object has to have excess charge and the other one not, or one point in a system. And so on Monday, we'll do this flow of charge. We'll do it with the Van der Graaf generator. And those of you that were in physics, we did it earlier. Some of you missed it, so we'll do it again for real this time with everybody there. Just don't ruin the story for the people who haven't had that part of physics yet. Okay, but what we'll do is we'll change it from charge building up on the Van der Graaf generator to charge flowing. Okay, now, like I mentioned in the last video, back years ago, they assumed that the flow of charge was positive charge flowing. They assumed it was what we would now call protons. Okay? And they believed that right up until 1908, 1910 area, when they found out the structure of the atom. And when they found out the structure of the atom, they realized those protons were stuck inside the nucleus. And when you scuff your feet across the carpet, you are not getting those protons out of the nucleus. It's the charge that's being transferred has to be the negative charge, the electrons. But they only figured that out years after they had been using current. They were assuming was protons flowing, positive charge flowing. And so when they figured out the structure of the atom, they were like, oh no, what do we do now? And they decided to do the only thing that they thought possible. Let's not tell anyone, and maybe they won't notice. They won't figure it out. But of course, it didn't take long for the rest of the people to figure out, wait, if this is really the structure of the atom, how is that positive charge flowing in current? To this day, we still find people using what's called conventional current. So if you ever hear me or anyone else talk about conventional current, it means they're assuming it's positive charge flowing in the circuit. Most electricians use conventional current. Most physicists and quite a few engineers use what's called electron current. In the end, mathematically, the way the circuit works, it makes absolutely no difference which one you use. So if I draw a circuit, and I think you know from Science 9, that's the symbol for a battery. Here's a resistor. The short side of in the battery symbol is the negative, and the long side is the positive. So for those of us who use electron current, the current would flow out of the short side through the resistor back to the long side. For the people who use conventional current, they would see the current coming out of the long side of the battery, flowing through the resistor and coming back to the battery. So the current has one way would have a positive charge, one way would have a negative charge. The electron is opposite, and those two changes just cancel each other out. Mathematically, absolutely no difference. I will tend to use, when I'm doing it, electron current. But when we get into magnetism, if you use conventional current, all the rules are right-hand rules, whereas if you use electron current, they'll be left-hand rules. And so when we do it, I will make you switch back and forth to make sure that it doesn't matter who teaches you next, you'll be able to handle the hand rules. Okay, so we'll talk about right-hand rules, left-hand rules. Rules are the same. The direction is just different because it depends on which hand. Okay, so we'll come back to that. What do you need to get current to flow? Well, you need a material through which it will flow. You need something creating a difference in potential. A few minutes ago I said, like, when you touch the doorknob, charge flows from you to the doorknob because you have more charge than it. And that's called a potential difference. That gets us back to that V we were talking about in the last video. Normally in a circuit, the battery supplies the V, the voltage, or the potential difference. Okay, and the other thing you need is a closed circuit. So on Monday when we do this, we'll have those three things and we'll create current to flow. You would have seen current in an equation in grade 9 science in what's called Ohm's law. V is equal to IR. Voltage is equal to the current flowing through the circuit times the resistance of the circuit. Current is measured in amps. Where does that come from? It actually comes from a different equation. The amount of current flowing through a circuit is equal to the amount of charge, Q, that passes by a particular point in a certain amount of time. Okay? So current is really equal to charge over time, which is coulombs, the unit of charge, over seconds. And that is equal to an amp. Really, the full word is an ampere, named after a buddy named Ampere, and its letter is a capital A. So current is measured in amps. Voltage is measured in volts, and you probably remember that resistance is measured in ohms. And the symbol for an ohm is a capital omega, a Greek letter. Okay? So if we draw a circuit, every circuit needs a potential difference, something to set up a potential difference, a battery, a power supply. Every circuit needs something like, it's called a load, a resistance. It could be a light bulb, it could be a microwave, there could be more than one in there. And every circuit needs wires to connect it. Okay? And this is where we would get Ohm's law. Again, from grade 9 science, you probably remember this is a this is a series circuit. And this would be a parallel circuit. Series circuit only has one path. Parallel circuit, it has a choice. It can go the current can go one of two different ways. Maybe the only other thing for right now you need to know in electricity is that there are two meters. One is called a voltmeter and one is called an ammeter. Whoops, that's MM, sorry, I messed up there and I can't see through I'm looking at it through the screen and not at the paper, and so it's hard for me to see. A voltmeter, circle with a V in it, measures the voltage or the potential difference in a circuit. An ammeter, a circle with an A in it, measures the current, how much current is flowing through a circuit, or amps. Okay, so I think that's probably enough for now on the preview review. On Monday, we'll just quickly go over a couple of things. We'll play with the Van der Graaf generator, and then we'll actually begin to start magnetism now that you have all that. I would like you to do some of the questions on the review sheet. I'll type it in the note to the class. Thanks, and enjoy your snow day and your weekend.